Now, as usual, with an op-amp in the circuit, I'm going to apply the op-amp rules first. Let me define a couple of node voltages, say VA and VB, and the op-amp says that those two voltages have to be the same. Now, let's do KCL at the input terminals as kind of a knee-jerk reaction. So let's do KCL at A, summing currents leaving the node, this current plus this current plus this current, which according to the op-amp rules is 0 amps. So VA minus 3 volts, if I take this as my reference ground, over 10 ohms, plus VA minus 0 volts over 5 ohms, which is the current in this direction, is equal to 0 because there isn't any current into the op-amp input terminals. If I solve this, multiplying through by 10, I get VA minus 3 plus 2VA is equal to 0, so VA is equal to 1 volt. If VA is 1 volt, then that means that VB is 1 volt. According to this rule here, now I can do KCL at B. So let me make my diagram a little bit neater. That's 1 volt. So current here plus the current here is equal to 0. So 1 volt minus 6 volts over 10 ohms plus 1 volt minus V out over 5 ohms, which is the current in this direction, is equal to 0. Multiplying through by 10, so this is minus 5. So taking that to the other side is 5, and 2 minus 2 V out is equal to 5. So V out is equal to minus 3/2 of a volt. Now, as usual, there's more than one way to do the problem. Let's clean this up a little bit and take another look at a way to do VA. Now, if I define this as a voltage, say V sub x, since this current is 0, this current has to be the same as this current, and this 10 ohm resistor and the 5 ohm resistor are in series. We know the total voltage across that series combination. We're finding the voltage across one of the resistors. We can use a voltage divider. So I can say that V sub x is equal to 3 volts times 5 ohms over 10 ohms plus 5 ohms, which is 1 volt, which is the same as we got for VA before. So if we go take this still becomes 1 volt at that terminal, and if we do this, we get the same answer.